Hi Year 11. Today we are going to make a start on our quantitative chemistry topic and we are going to turn to page 128 in our booklets. Now we are going to need to be able to compare the masses of different atoms and molecules, and in order to do this we are going to need to be able to work out how many neutrons an atom has. We are going to define the relative atomic mass and we are going to calculate the MR, or the relative formula mass. Now, the first thing that I would like to remind you of is the definition for isotopes, and we've already covered it, but we're going to write into the top of the page that isotopes are atoms of the same element that have the same atomic number but different mass numbers. Now, if we consider the element hydrogen, hydrogen has 3 isotopes, and you can see that we have got hydrogen 1, we have got hydrogen 2, also called deuterium, and we have hydrogen 3, also called tritium. Now, if we look at these isotopes for a moment, you can see that each isotope has a bottom number of 1. We've already learned that this is called the atomic number. Now, the atomic number tells us 2 things. It tells us the number of protons in that atom's nucleus, and because all atoms are neutral, it also tells us the number of electrons. Remember, protons have got a positive charge, electrons have got a negative charge. If the atom is going to be neutral, we need to have the same number of protons as we do electrons. Now, if we look at the top number, and we've already learned that the top number is called the mass number. Now, the mass numbers for each of the isotopes are different. And remember, the mass number tells us information about the nucleus. So the mass number tells us about the number of protons added to the number of neutrons in the nucleus. So if I want to work out the number of neutrons, I take the bottom number away from this top mass number. So this first isotope will have no neutrons. The second isotope, 2 take away 1, will have 1 neutron, and the third isotope's 3 take away 1 will have 2 neutrons. So consequently, I can add to my definition that these isotopes have different numbers of neutrons. Now, if I were to think of the actual mass of one of these hydrogen atoms, it would have an actual mass of 1.7 times 10 to the minus 24, which is absolutely tiny. Far too small a number for us to easily get our head round and for us to easily use. So therefore, rather than use actual masses of atoms, we use this relative atomic mass. Now, we have met this definition before, but we're going to spend a little bit of time just revising it. Now, the relative atomic mass must take into account the abundances of different isotopes. Now, if we consider the element chlorine. Now, if I were to go to the periodic table, I would find that chlorine's top number, its mass number, which is also its relative atomic mass, is listed as 35.5. Now, it's not a whole number because it's got to take into account the abundances of the different isotopes. Now, chlorine, like you can see, has 2 isotopes. We have chlorine 35 and we have chlorine 37. Now, if I had a sample of chlorine, the amount of this chlorine 35 in the sample would make up 75%. The rest of the sample then would be chlorine 37, and 25% of this chlorine 37 would exist in my sample of chlorine. Now, if I were to work out chlorine's top number, its relative atomic mass, I have got to take this relative abundance into account. So 75% of my sample would be chlorine 35. Add it to the rest of the sample, and there's 25% left, and that would be chlorine 37. Now, I divide by the total abundance, which always adds up to 100, and I would find that chlorine's relative atomic mass comes out as 35.5 because it's weighted towards the chlorine 35 isotope, because naturally there is more of this chlorine 35 isotope. And we spent some time at the start of year 11 working out these relative atomic masses. Now, in my definition then for the relative atomic mass, I've got to take this into account. And if we look at the definition, the relative atomic mass, and another way to write that is the AR, is the weighted mean mass, i.e. it's got to take into account these isotopes of an atom of an element. Now, we also know that we compare all atoms of all elements to 1/12 of the mass of an atom of carbon 12. But I am going to discuss the second part of this definition just now. But for now, you're going to write the definition in to page 128. Now let's think about the second half of the definition. We said that it was compared to 1/12 of the mass of an atom of carbon 12. Now if we think about an atom of carbon 12, you can see on the screen that we have got in the nucleus 6 protons and 6 neutrons. We know that this carbon atom is neutral, so therefore in the shells around the nucleus we've got our 6 electrons. Now remember, the mass number, the top number, is all to do with these protons and neutrons. So an atom of carbon has a mass number of 12, the protons and the neutrons added together, and an atomic number of 6. Now we pick carbon as the standard against which all other atoms are compared. So if we take 1/12 of the mass of an atom of carbon 12, so if we take 1/12 of 12, well that's 1, and then we're comparing all the other atoms to this atom of carbon. Remember, we're not taking the actual masses, we are using these relative masses because the actual masses are far too small for us to be able to use effectively. Now if we consider the periodic table then, we say that an atom of carbon has a mass of 12, and then I can compare everything else to it. If I were to go and pick an atom of magnesium, it's got a relative atomic mass of 24, so I can easily see by comparing that an atom of magnesium has got twice the mass of an atom of carbon. If I were to think of nitrogen, I could see that an atom of nitrogen is just a little bit heavier than an atom of carbon. Hydrogen is the lightest element, and I can see that it's 12 times lighter than an atom of carbon. So these relative atomic masses provide a good way for us to be able to compare the masses of atoms without using the actual mass. Now it's quite a long definition, but in the exam it's worth quite a lot of marks, so it's well worth learning the definition for this relative atomic mass. Now what we have got to be able to do in this unit is we've got to be able to use these relative atomic masses, and we've got a task on page 128. Now you will need to have your periodic table handy, and you've got one in at the start of your notes. Now we're asked to find the relative atomic mass, the AR, of the following elements. And remember, AR is just another way to write relative atomic mass. Now what we are doing is we're going to the periodic table and we are just finding the top number. So the relative atomic mass, the AR, and the mass number are really all the same thing. So you can pause the video as you need to, write in the top numbers, and then check that you're correct against the video. So hydrogen has a relative atomic mass of 1, sulfur is 32, carbon 12, oxygen's top number is 16, nitrogen is 14, calcium is 40, aluminium is 27, magnesium is 24, lead is 207, helium then has a relative atomic mass of 4, sodium 23, phosphorus 31. We've already chatted about chlorine. It's 35.5. And the last one, copper, then, has a relative atomic mass of 64. So we're really just going to our periodic table and we're picking out the top number. Now, that works well if we have got elements, but sometimes we need to consider the mass of compounds or molecules. Now, when we are talking about a molecule or a compound, we work out the relative formula mass. And the relative formula mass can also be written as the MR. Now, it is the total of the relative atomic masses of the atoms in the numbers shown in the formula. So if we look at a couple of examples, because examples always make things more simple. So we are asked for the MR of carbon dioxide, and we're given the formula of carbon dioxide as CO2, but it would be one that we know already anyway. Now, in carbon dioxide, we have one carbon atom. We have two oxygen atoms. So what we need to do is we need to total up the relative atomic masses of these atoms, and we've got to take into account the number of atoms in a molecule of each compound. So I have one carbon. Carbon's relative atomic mass is 12. So 1 times 12 is 12. We have two oxygens, and remember it's the top number, the relative atomic mass of oxygen is 16. So 2 oxygens, we've got a total of 32. Now we're going to add these up to find the relative formula mass of carbon dioxide, and that totals up to 44. We're going to apply the same process to ammonia. So ammonia has the formula NH3. We have one nitrogen atom in a molecule of ammonia, and we have 3 hydrogen atoms. Now again, I'm looking at the top numbers, and I'm finding nitrogen's top number, its relative atomic mass is 14. Hydrogen, again, I'm looking for hydrogen's top number, its relative atomic mass is 1. We've got 3 of them, so 3 times 1 is 3, and when I add them together, I find that the relative formula mass, the MR, for a molecule of ammonia is 17. Now folks, we need to practice this. So you have got some more of these to do on page 129 and at the top of page 130. Now I'd like to spend a little bit of time discussing the extension at the bottom of page 130. Now we are asked to use our data sheet, that's our periodic table, not forgetting about the back of it as well, to work out the formula of the compounds below. Then we're asked to work out the MR of the compound. Now number 15, we have got iron 2 sulfide. Now this 2 in Roman numerals gives us the valency, remember, of the iron. So in this compound, iron has a valency of 2. Now we have got iron sulfide, so in this compound we must have some sulfur. Now we don't know the valency of the sulfur off the top of our heads. We've got to go to the periodic table and we have got to find the valency of this sulfur. Now if we find sulfur, we find that it's in group 6. Remember, that tells us that an atom of sulfur has got 6 electrons in its outer shell. It will need to gain 2, so therefore its valency is 2. The 2 and the 2 will cancel out to 1 and 1. Hence, when I cross and drop the valencies, I will find that the formula for iron sulfide is FeS. Then it's just a matter of going and adding together the top numbers to work out the MR. So if I were to do this one example, iron's top number in the periodic table is 56. Sulfur's top number then is 32, and I can add them together to work out that the MR of this compound then is 88. But I've got to work out the formulas using this cross and drop rule that we learned earlier on in year 11. Now, if we look at one more of the formulas, ammonium chloride is the second compound. Now, ammonium chloride is formed from the ammonium ion and a chloride ion. Now, the ammonium ion is found at the back of the periodic table, and it has a valency of 1. Chlorine is found in group 7. It needs to gain 1 electron, so hence its valency again is 1. When we cross and drop then, we find that the formula for ammonium chloride is NH4Cl. Now you need to apply the same process then for each of these formula. I am going to complete the formula now, so you can pause the video and try it, come back in a few minutes and make sure that you've got them correct. For aluminium sulfate, its valency is 3. A sulfate ion is found at the back of the periodic table with a valency of 2. When we cross and drop then, we find that the formula for aluminium sulfate is Al2. Remember that sulfate is a molecular ion, so we will need brackets to say that the whole sulfate ion is getting multiplied by 3. Potassium hydroxide then, potassium has a valency of 1. The hydroxide ion is found at the back of the periodic table, also with a valency of 1. So when we cross and drop, I meant to write 1 rather than a positive. When we cross and drop then, we find that the formula for potassium hydroxide is KOH. Lead chloride then, lead's found at the back of the periodic table, has a valency of 2. Chlorine's found in group 7, hence a valency of 1. When we cross and drop then, we find that lead chloride's formula is PbCl2. I don't need brackets because chlorine is not a molecular ion. There's only one element. There are not 2 capital letters. Remember, molecular ions are made up of 2 or more different elements. There will always be more than 1 capital letter in its formula. The last one then we're left with is silver nitrate. So silver is found at the back of the periodic table with a valency of 1. A nitrate ion, again found at the back of the periodic table, has a valency of 1. When we cross and drop then, we find that silver nitrate's formula is AgNO3. Now don't forget to finish off numbers 15 to 20 by working out the relative formula mass, the MR, of each of the compounds.